So hello everyone, I'm Hariharan Krishnan. People call me Hari. So I'm the SK signal processing domain specialist and also the SKLO CSP, which is the Central Signal Processor Design Authority. Today I'll talk about an all-sky imaging correlator that I worked on for the last couple of years and describe its working and show you some results from the commissioning on one of the long wavelength array stations, and just finish up with a summary of where it is at and what's happening with the project and how it may be relevant for Argos as a all-sky imaging backend. Mm, so except for the slide and probably the last and the templates, much of the talk does not exactly reflect what's happening at SK in terms of signal processing. So yeah. So the motive, so here's a broad outline of the talk. So I'll give you a motivation for this particular project and walk you through the basic radiator interferometry and conventional correlator concepts and how the real-time imaging that I'm going to describe here in this talk is different from the conventional correlators, and just show you how the optimization happened, the commissioning results, as I mentioned, and finish up with a summary. So the motivation for this project was derived from the scientific requirements and the technical requirements. So there's now an interest in doing H1 intensity mapping science with sensitive radio arrays, and most of these arrays require a compact configuration with large number of antennas, at least on the order of thousands or so, and um, and of course low frequency radio transients like FRBs and meteor afterglows and so on. And they have observational study of stellar flares like on sun-like stars and dwarfs and so on, and star-planet interactions. And the technical requirements, of course, to achieve these is primarily to increase the surface brightness sensitivity, wide field of view, and larger telescopes for high angular resolution. And all of this relies heavily on the signal processing techniques that we develop with the advent of relatively easier availability of GPUs and FPGAs and so on, and high-speed sampling. So, a real-time imaging concept is more ideal at a wide frequency range with high temporal resolution to achieve these, particularly the transients and other science goals. So that's the primary motivation for this work. So when you talk about radio interferometry, it's really not easy to pass on without describing the two-element interferometer, which is the fundamental unit of any radio telescopes at this point. So you have a pair of antennas separated by a distance, and you sample you record the voltages from those antennas, and then what you essentially do is perform a cross correlation operation, which is the multiplication and integration of those voltages to measure what are called the visibilities. So we measure multiple such visibilities with a wide range of antenna pairs, with sampling the sky at different spatial scales. And using those visibilities, we try to synthesize the sky and synthesize an aperture, and then try to get the map of the sky. So conventionally, how this done is, so we do it with what are called the FX correlators. Basically, when you do that, the same multiplication and integration in frequency domain over a certain period of time. So it's started off with implementing in analog correlators, and then to ASIC-based systems and FPGAs, and now we are more into the GPUs like XGPU and Tensor Core correlators and so on. So this is fine as long as the number of antennas is, let's say, on the order of tens of antennas, let's say 25, 30 or so on, like in GMRT or VLA. And when it goes higher, like in the case of NWA or LOFAR, or even now with the SKA, when the number of antennas involved is quite large, and the number of the complexity of the correlator itself gets larger, which increases the computational needs, and of course drives the cost of your backend. You know what kind of backend you need, so whether you need FPGA-based accelerators or GPUs and so on. So in view of this, so what we have been working on is a novel imaging algorithm called the E-field parallel imaging correlator. So what it does is basically, so you have the visibility function that's recorded from the cross correlators that's given by the equation 1, which is related to the sky illumination pattern convolved with the antenna sky intensity distribution with convolved with the antenna illumination pattern, and essentially it's just a two-dimensional Fourier transform. The equation 1 is basically for a planar array where you ignore the third coordinate. And this essentially, from here, you go to the sky intensity maps by inverting by an inversion of Fourier transform and deconvolving it. So what you have in equation 2 is basically the dirty image, the intensity distribution of the sky. So the MOF formalism, or the modular optimal frequency Fourier formalism, that EPIC bases itself on, is a rearrangement of equation 2 to show you that the the visibility distribution can also be essentially rewritten as a convolution of the uh, direct voltages or the electric fields that are recorded with the antennas with a gridding function called W, and that can be still integrated. And the EPIC image output would be a simple Fourier inversion of that, and that's what you see in equation 4. So for more details of this math is described in the detail technically in Krishnan et al. 2023. That was published early this year. And for more details, you should look at Tyagarajan et al. 2017 and Morales. So this is the fundamental of mathematical formalism that EPIC is based on. It's called MOF. So it's basically a direct Fourier imaging concept. So it's ideally suited for real-time imaging in large and very compact arrays. I'll tell you why it's specifically suited for compact arrays later on. So it's based on the concept of modular frequency Fourier, which is a simple mathematical formalism of direct Fourier imaging. So what we do here is essentially instead of performing a cross correlation and getting to the visibility space, we directly grid the electric fields from individual antennas onto a regularly spaced XY grid based on a nearest neighbor algorithm, and then take a spatial two-dimensional Fourier transform, and you get to the sky plane. And essentially, you're synthesizing the aperture on the fly. So what happens here is there is a reduction in the computational scaling from what you would have with the n squared for number of antennas to n times log of n from the Fourier transform for the number of grid points that you use for getting the voltage gridded. So this reduction in computational scaling is extremely useful, and it's not something that it has been attempted before with the MIT UR experiments with the omniscope and the best arrays and so on. The only difference here with the MOF is that MOF does not assume a regularly spaced or a regularly spaced array, or it's not a requirement that you should have redundant baselines. So there's room for heterogeneity for the antenna spacing within the array, and that's where MOF relatively sells better compared to the other two techniques or previous techniques that's been employed. So EPIC in a nutshell. So you get the electric fields measured by the antennas. You take a Fourier transform, get to the frequency plane, and you have a frequency and time 2D electric fields that are measured for each of the antennas. The calibration does not yet happen. It's something that's envisioned, but this two-dimensional space of frequency and time distribution of the electric fields is then gridded onto a regular grid using the nearest neighbor algorithm based on the antenna location. So the essential part here is that the individual antenna's location as precisely as possible. And once you know that, once you've gridded the voltages, then you take a two-dimensional Fourier transform, then integrate that, square it, and you get the imager. and you get the image output, a time averaged image output. So what's the advantage here? And in compared to the conventional FX imaging and doing a similar Fourier transform, because there is a Fourier transform involved once you grid the visibilities, is that the time scale on which you are able to do this is much almost at least 1,000 times faster than what you would do with the conventional FX correlator, as I'll show you. Um, so the Epic has been mostly developed using the long wavelength array, which we use as a test bed for the Epic case. So LWA is a couple of stations, two independent antenna stations, which are very small compact arrays. So each of these stations consists of about 256 dual polarized low frequency antennas in the frequency that operate in the frequency range 10 to 88 megahertz. And the dipoles, as you can see, are distributed in a very random fashion so that you reduce the side lobes and other stuff. And these two arrays mostly operate essentially as phased arrays with multi-beamform capacity. So you can form up to multiple 3 simultaneous beams and do pulsars and solar signs and so on. So we use the LWA for mostly testing the correlator for the EPIC. So it's a collaboration between the University of New Mexico, Arizona State University, and a couple more people from different universities in the US. So it's implemented on what is called the Bifrost streaming framework. I should have attached the GitHub link for this. Anyway, so the Bifrost framework is mostly a C++ and the Python-based streaming framework that's used. So the idea is to use it as a streaming platform, not just as a streaming platform, but also to build standalone FPGA or GPU systems. So you can actually build different pipelines. You can make a spectrometer, you can make a correlator, or whatever you want with just this framework. It consists of it provides you CPU support through CUDA APIs from the NVIDIA that's integrated in the Bifrost framework, and it consists of concepts called blocks and ring buffers. So any functionality that you would like to implement is implemented as individual blocks, and each of these blocks are connected to the other through ring buffers, so that that ensures smooth flow of data in real time. So many systems are actually built at the LWA using this Bifrost. So you have Lassie, which is the LWA All-Star Imager, and Wilbur, which is a real-time pulsar backend that's implemented pulsar de-dispersion backend that's built pulsar de-dispersion and integration backend that's built with this pipeline. And then you have Epic, which is a standalone system that's commensally installed at the LWA Sevielta site. So that's the station that's located in New Mexico. Both the LWA stations are in New Mexico, one that's co-located with VLA and the other at a national park that's about 75 kilometers from VLA. And the network topology is defined by the advanced digital processor subsystems. So how the data gets in. So you have the data digitized through Roach 2 boards, and that gets to what's called and a raw F engine is built in the Roach 2, and then you also get a beamformed data that's again it's a raw voltage data. It's actually a Fourier transformed, slightly integrated dynamic spectral data, and you have a transient narrowband buffer. So you just choose about a very narrow band of 3 megahertz or so, and you can store the raw voltages. So the F engine can support an overall bandwidth of about 19.8 megahertz. And this 19.8 megahertz is divided into 12 streams, approximately 3.3 megahertz each. And these streams are flown through to Lassie and Wilbur and Epic. So that's how the distribution of the data itself happens for the F engine data. And what we essentially do is use one of this F engine data. mm, that stream we actually get about so it's more like all of this 12 stream all of these 12 streams are available via this 40 gig link, and the Epic machines can subscribe to one of those streams, one of those subbands. So each subband consists of about 132 frequency channels with the frequency resolution 25 kilohertz and time resolution of 40 microseconds. And that's the data rate, data volume that goes through this link. And you get all the complete dual polarized complex spectra from all of each of the individual antennas through the streams to the EPIC machine. And what happens here is we perform a decimation in frequency. You still divide it into, that's what happens in the multicast UDP packets. You get the streams. You perform a basic delay correction. And once the delay correction happens, you grid the voltages. As I mentioned, you grid the individual voltage values for every frequency channel, every timestamp, one for every antenna. So you have basically an X and Y grid for both the polarizations in voltage grids, and the grid is chosen such that it's accommodated on the GPU, and also the the positions of the gridding of the voltages is chosen based on a nearest neighbor, based on the location of the antennas in the array. And then you take a Fourier transform of this voltage grids and perform a grid multiplication to get the cross polarized voltage grid. So now you have a full polarization grid. So you have a autocorrelation grid for the two polarizations and the cross for the two polarizations. So you basically have four grid outputs, and then perform an autocorrelation removal. So you estimate autocorrelation using the raw voltages. You estimate an autocorrelation grid, and then subtract the grid so that you essentially remove the offset and other problems. So this is basically done to reduce the noise, self noise from the antennas, from the receiver system itself. So there are two modes that EPIC supports. One is offline using the narrowband voltage data from the ADP, and the online mode where we use the F engine data in real time. So you have two options to operate EPIC. One is an offline. You can just so that's useful to compare it with other cleaning and imaging algorithms like in CASA. Uh, here's the first light that was implemented. What you see here is basically a transient, a meteor reflection transient that's shown here at close to the minus 30 declination. So the first light was achieved in 2019 with a very limited hardware resources. So you could only image about 100 kilohertz of band on a single GPU. And after the first deployment, we performed some optimizations in terms of firmware and also in hardware. So what you see here is a comparison of what the optimizations have done. So we have so the essential function that we optimized was the gridding, because that's the most computationally intensive part. So we had what was called a Romain gridder, which is basically uh, a, a, um, a gridding strategy on GPUs to make it more efficient for real-time imaging with cross correlators. So we adapted it for EPIC, where instead of gridding visibilities, we grid the voltages. So we adapted that method for the first version, and we found that it wasn't really an optimized version for EPIC. So I performed some optimizations to improve the speed of gridding, as you can see, by almost a factor of 2 in terms of frequency channels versus kernel processing time. So and also in terms of number of grids, number of the grid size that can be processed with the voltage gridding kernel or the block. And here on the middle, you see middle column, you see the comparison for a grid multiplier. So you actually multiply the two grids, right? So Bifrost enables you to implement standalone algorithms using a specific map function, mapping kernel or mapping block that's available as an inbuilt solution in Bifrost. So we optimize that to implement a voltage gridder that's very specific to EPIC, and you can see that we improved the performance, and again in terms of by a factor of 2 in terms of grid size that's processed per kernel processing time, and also the number of frequency channels we could process now with EPIC. It's almost it's slightly more than twice the amount. This is because we enabled additional memory that's available for processing compared to the earlier implementation. And through these optimizations, we were able to increase the bandwidth from 100 kilohertz to about 1.8 megahertz for a 64 grid size. So what you see here is an image of the sky with the sun, doing something. It's probably bursting there, and the data volume that you get with Epic is estimated to be about 100 GB per hour. And you have raw frames you have raw voltage frame, that's the voltage grid that happens there, that's about 40 microseconds. And this image is about 1 second integration with 1.8 megahertz band integration, and you get accumulated images for every 82 milliseconds or so. So that's the speed with which we get the image output. So what you get from Epic is basically the dirty image, and you still have to do the cleaning and stuff. So we validate this Epic images through simultaneous beamformed observations. So what you see here is a comparison of the Epic dynamic spectrum for the sun, extracted from the pixels corresponding to the sun for about a 1 or 2 minute period, where you see some very faint bursts from the sun on the top dynamic spectrum, and the bottom you have a comparison for the same time with the beam, because beam is the one that's normally used. So we use that to validate the result. And what you see on the right is a band integrated light curves for the epic and the beam that's shown on top of each other. You see this difference mainly because I think it's the way that I think it's the way the noise gets reduced or something. So that's what we understood from the epic and the beam difference. So what you see here is a difference. Like it's not too high. It's pretty good. Um, yeah, so that's how we validate the epic and epic images, epic spectrum. So once we do that, we also managed to observe some pulsars, some bright low DM pulsars, because we are looking at low frequencies, almost at 30 megahertz or so, 35 megahertz or so. So we had to go for a very low DM, like below 20 per cc, and we look at very bright pulsars so that we know that we actually get the profiles right. So what you see here is a snapshot image of the sky during the observation. So you're actually seeing so you have multiple pulsars in the field, but here we are just looking at the bright ones. So I've marked them on the image here. It's at the I think it's about I think it's this was at 38 megahertz. And what you see here on the right is you take multiple images over a period of 45 minutes, and then extract the light curve, extract the dynamic spectrum and the from the images for the pulsar locations from each of those images over the 45-minute period. Perform a de-dispersion, incoherent de-dispersion, and then the average profile looks like this. So you can see so this is not exactly the pulse profile of the pulsars, but just to demonstrate that Epic through Epic we are able to do pulsar detections and so on, and it's essential for transit detection, as we also were able to capture at least a few giant pulses from this bright pulsar B1133 plus 16. So it demonstrates how Epic can be an ideal backend for not only observing the full sky, recording the full sky as a continuum image, but also to observe and localize transients to first order. So this can be a very useful backend for compact arrays, but essentially for survey telescopes like DSC 2000 and so on. So that's the idea with which Epic was implemented and tested, and so we have proof of that. So okay, I'm supposed to see yeah. So this is my last slide. Sorry. Oops. Yeah, so this is my last slide, the summary slide. I'll leave you there. So we basically commissioned Epic as a commensal backend at one of the LW stations where we test and develop. And the current version of Epic can produce 128 cross 128 image grids at a cadence of 40 milliseconds and for a bandwidth of about 3.2 megahertz, not 1.8, on a single GPU. We are currently using a NVIDIA GeForce RTX. So there's now plans to increase this bandwidth to 20 megahertz with more cards. Probably 5 more machines are set to be added at the site. And as you can see, this can be a quite an efficient imaging backend for compact arrays like Hyrax and Argos and so on. I think I envision. I think Argos is also going to be a compact array, given considering the specs that was discussed yesterday. So yeah, why is it more efficient for compact arrays? Is because of the FFT that's involved in the gridding. So when the FFT when the grid sizes get large, so when you compare the computational speeds of a traditional FX and the EPIC gets beat down by the FX correlator itself. So it's essentially the arrays, as the array size increases, your grid size also increases, and FFT's n log n scaling is what EPIC relies on for its efficiency, and that's where it gets speeds on, and that's why it's more suited for compact configurations. Probably it can be it can be essentially it can be an efficient it can be a useful tool for all sky imaging with a single station of SK or something like that. So yeah, I think I'll leave you there. This is a movie which shows you. Okay, not able to show that. Yeah, I'll leave you there with the movie. It's a 14-second capture from the live stream that's implemented now. So yeah, that's it. Thanks.
Okay, thank you very much. So questions? Ewan?
Yeah,
Go ahead.
loads of questions. This is really, really interesting setup. I think that the thing to understand how something like this maps to a project like Argos, the thing that wasn't clear to me from your presentation was you said that as the array size and maximum baseline increases, then your grid density increases and the computation goes up. Surely that's also the case as you go up in frequency. So does this technique map to telescopes operating not in these very low frequency bands like the LWA?
That is true, but then here, so what happens is in this case, the reliance on the speed in comparison to FX is on the FFT speed itself. So it's so the gridding is the gridding needs to be faster for the higher frequencies there. So the computation for the gridding increases as the frequency increases, where you're right. So I think that's where we are actually trying to focus how we are going to tune the efficiency of Epic, and that's how we were able to get to 128 cross 128 on a single GPU. This is only on a single GPU. So surely when you talk about higher frequencies and larger bandwidth, you're going to have more GPUs or or other backends that you choose to bring in. So the FFT is what ultimately decides the speed or the effectiveness of the imager itself here in this case, because you have to grid, and then you have to grid the raw voltages. So the gridding and the FFT together is what decides the computation. But
So
the gridding,
do I understand this correctly? That there's no accumulation step. You're basically you're gridding for every sample that comes to the telescope,
yes,
and then you do the FFT for every sample. So there's no accumulation, so there's no amortization of the cost there. But the trade-off is that you get extremely high resolution, high time resolution imaging, right?
yes, extremely high time resolution. That's right. So one way, so here we are doing it at 40 milliseconds. So one way could be something like I think that's the trade-off there. You get the higher time resolution for Epic. compared to what you would get with an FX. So for the same frequency, what you would get from the current Lassie or other all sky imager that's already used there at the observatory is about 10 seconds. So which is a huge gain there.
So just to confirm, so you do expect that the grid size goes, as you go to higher frequencies, you should have a finer grid, right? Otherwise you get
That's true.
defacing.
That's true. So
Yeah,
that's
so I
that
mean, just a
that's
back of the
yeah
envelope calculation here
that's the
says that,
reason. Yeah, so that's the reason we wanted to go for 128 cross 128 in this case, because
right,
initially we had a 64 cross 64 grid size, and we were limited to frequencies below 45 megahertz.
okay.
And we now wanted to increase that to almost like we are actually looking at we are looking to increase it to 256 cross 256, not exactly 128. The 128 is what we achieved now. So 256 because we want to cover the entire LW band. So as you go for higher frequencies, obviously this grid size is also going to increase. And the advantage of EPIC is that uh, as the number of antennas and the number of grid points, it's based on the grid points. So as the number of grid points increases, you're also uh, using the GPUs or the computational resources more efficiently. So GPUs scale better when you have larger number of points. So that's the advantage. So although we haven't tested it, we expect that that's going to be better. But I think there is a comparison that was made in simulation for between FX correlator and EPIC that was done by Tyagarajan et al. 2017. So I haven't attached the plot here. I should have done that. So that clearly shows you where exactly the FX gains over EPIC or EPIC gains over FX. So that shows you beautifully how on the computational scaling itself, EPIC EPIC wins out.
Yeah, I need to look that up, because my gut instinct for that would be that despite the fact that you are putting more data on the GPU, the FFTs themselves are an inherently less efficient operation because of the memory constraints on the GPU compared to just a direct cross correlation, which can now be done with tensor cores extremely efficiently.
Mm-hmm.
But this is interesting. Thanks.
So just to follow up on Yuan's question, so would there be any advantage at higher frequencies if you had some redundant baselines in your array?
I think the redundancy is mostly for calibration purposes. So most of the compact arrays that are coming up, like for example Hera or Hyrax, so the focus is on having as much redundancy as possible, so that it can be calibrated as easily as possible. So that's the idea. So I think having redundancy, using that redundancy, you can actually, it helps you calibration. So here in this case also for real time, so calibration is the challenge in this kind of real time imaging concept. So we are still figuring that out, how to do that. But I believe the calibration is what motivates for redundancy in arrays. So that shouldn't really affect your imaging itself, because MOF does not care about the array layout as such. It does not have a constraint there.
Okay, thank you very much. Any other questions for Hari? Okay, if not, thanks again.